Friends, welcome back. New little sequence of videos, circular motion. We're actually doing a bit of a callback to velocities and accelerations, forces that we saw earlier on here with the scenario that we're dealing with objects that are moving in circular kind of paths. Anything from whirling around a ball on a string, to a car making a turn, to objects orbiting things in space. All those fall into the category of circular motion. In this video, we're just going over, of course, the very beginning, the basics, looking at speed, velocity, and acceleration, something known as centripetal acceleration, all right? Now, for the most part, not always, but for the most part in this sequence of videos, we're talking about something known as uniform circular motion. And the definition of that is really just what it sounds like. It's us saying, let's have an object that's moving in a circle, okay, a nice circle, and it's traveling at a constant, at a uniform speed. It's not speeding up halfway through and slowing down the other half. It's moving at a constant speed in a circle. Now, we will see some examples, especially for vertical circular motion, where that's not true. But for right now, especially in this video, we'll assume, and we'll often assume, that things are moving in a circle in a nice, easy, uniform way. That's uniform circular motion. All right? So, let's get into some key ideas. First, average speed. That's kind of how we started the very beginning of this sequence of videos talking about average speed. We know that average speed is just an object's distance divided by its time. Well, for a circle, if it's going around a circle, the distance is the circumference of that circle. That's what I have written right here. And the time would, of course, be the time to travel that circumference. Well, what's the equation for the circumference of a circle? It's 2 times pi times r, where r is the radius. So right here in this little diagram, imagine this is almost a classic, an older style toy. It's a little toy plane, let's say, on a string. And this kid is holding on to the string, and then they're spinning themselves around in a circle. They're going around and around and around so that this plane is moving along this string, being pulled in a circle. So the radius of the circular path that this toy plane is moving in is labeled r, or maybe I should have used lowercase r, but whatever, you get the idea. Okay, that's the radius of the circular path. The circumference, the distance traveled, 2 pi r divided by t. Okay, this is often written as an equation. I know they use v. To be honest, speed and velocity, it almost has to do with semantics. We're not really going to worry about it too much, but for this really basic average equation, you would see it written pretty commonly as this, 2 pi r divided by t, where there's that uppercase T again, because it's not just any time, it would be the time for one complete circle, okay? Now, to be honest, we don't really talk about average speed much. It's helpful because if we started off with just the idea of velocity, we know that velocity actually has to do with displacement, and you might have been confused being like, well, wait a minute, Thrasher, when you go from this location here all the way around, your displacement is 0, so your average velocity is 0. And that's kind of true. So talking about the overall average velocity of an object moving in a circle, again, it's semantics more than anything, but it kind of gets weird and confusing. That's why the word speed is often used here. But when we're talking about this plane's motion, velocity is important because, of course, it's not just moving, it's moving in a particular direction, and that direction is changing. So a common phrase, which, if it's uniform circular motion, it might end up equaling this, but these are not always the same thing. It's tangential velocity, written like this, v with a little t, t for tangent. And tangent means, well, it's a line that's just touching a circle in one location. And the velocity of this plane, taking direction into account, is tangential. What do I mean by that? Well, of course, this plane is moving around and around and around, but let's say we could pause this motion for just a moment. The plane is right here at this location, right? Right here, I put this little blue dot. The next nanosecond, it was here. The next spot, it would be right here. Well, from here to here, again, milliseconds, nanoseconds. That is a line that's kind of like that. That's the displacement from here to here. That would be tangent to our circle. I apologize, I won't be able to draw very well. Let's look right over here. The plane is at this location, and then one moment later, it'll be at this location. Well, in that short amount of time, what's the displacement? How is it moving? It's moving in this line that's tangent to the circle. So it's almost more akin to our instantaneous velocity. Remember that? The direction of the velocity of this toy, it is changing, and we'll come back to that in a little bit. The direction is always pointing tangent to where it is in the circle. So here, right here, v tangent. At this location, v tangent is like this. I could even go right here. V tangential, it's right here in this direction, okay? If we could pause this motion, whatever it is, car, plane, moon orbiting the Earth, okay, the direction of the velocity at any moment, it's tangent to the circle. So tangential velocity is often what we're going to be seeing in equations coming up, because that's truly incorporating the direction of the motion, okay? Okay, so we've talked about kind of displacement and distance and speed and velocity. The next part is acceleration. And when it comes to circular motion, we're dealing with something known as centripetal acceleration. I'll come back to that first word, centripetal, in a little bit. But acceleration, is this object moving in a circle? Is it accelerating as it's moving in a circle? Yes. Even though it has a constant speed. Again, maybe if we make up a number, it's 5 meters per second. That's the speed, 5 meters per second, 5, 5, 5. Remember, the motion is constant, that uniform circular motion. So it's always 5 meters per second in all these locations. But the direction is changing. That's important. The direction is changing. Every time this object is moving around and around. Look at those vectors. Those vectors are changing direction. Direction changes. That means the velocity, which is a vector, that means velocity changes. And therefore, if I have an object that has a changing velocity, it's accelerating. Objects, even if the speed is the same amount, because the direction is changing, it is in fact accelerating. Now, okay, the velocity vector is changing as it goes around. What's the direction of this acceleration? Let's figure that out. Now, remember, acceleration is a change in velocity, like this, or v minus v naught. You subtract the final velocity from the initial. Let's call this velocity b right here, and this a, because the object is swinging around like this, kind of going counterclockwise. It's at a first, then at b. If I wanted to figure out the direction of this vector, well, I could subtract the vectors of the final velocity, that's b, so that would be vb minus va. If I can figure out the direction by subtracting these vectors, I can figure out the direction of the acceleration. Now, vectors are a little weird. When you are subtracting vectors, you are actually adding their opposite, minus VA. Okay? This is important, not really so much for the AP exam if that's what you're studying for, but in understanding how we're going to get this direction for the acceleration vector. Okay? I'm trying to figure out the difference in these two vectors, this vector here pointing down into the left, this one pointing down into the right. Okay, acceleration is going to be the difference, but for vectors, the way you do that is you add the opposite of the second. And, this is the same in math and algebra. Okay? How do you add vectors? Do you remember something known as like the heads to tails method? If I have vector 1 and then vector 2, vectors 1 plus 2, I do this heads to tails method where I draw one, then the other next to it, kind of attached, and then the result, this dashed line, this is the result. This is the combination. I want to do this same thing, but for these two vectors right here. Okay? Now, I'm adding the opposite of A. So vector B, I'm just going to draw this velocity vector. It looks like this. Bum, 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 bum. What I've drawn right here is vector B. And then, because I'm truly subtracting it, that means I want to add the opposite. Vector A should go like this, in this direction, but I'm adding the opposite, so the opposite would be pointing this way. See, again, the actual velocity direction of A is down and to the left, but I'm adding the opposite of it. The opposite is just you flipping it, so that's up and to the right. That's what I have right here. And the result, bam, 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 this is the change in velocity. That is the acceleration. What direction is the acceleration? I have to change color, sorry. It's towards the center of the circle. It's to the right. In fact, that's what this term centripetal means. Centripetal means center seeking, center seeking. And that's because, I know I just did it for these two, but if you try and do this vector addition or vector subtraction, okay, if you're trying to find the direction of acceleration for objects moving in a circle, the direction of the acceleration is always pointing towards the center of the circle. That's why this is known as centripetal acceleration. Some people say centripetal. I don't think it really matters. I often say centripetal. But what's important, the direction of acceleration is towards the center. My last slide is really just kind of saying that again and introducing an equation. So here's that centripetal acceleration. I just got rid of that vector work. Okay, centripetal acceleration is often written with an A with a little c as a subscript, so acceleration, but what type? Centripetal. Right here is the exact same scenario I described in my last slide. I just found an image online, but it's showing the same thing. Here they are adding velocity 2, the final velocity, with the opposite of velocity 1, because acceleration is final minus initial. And in this case, even though they're doing it at kind of these two weird locations, when they do the subtraction, what do they get? The result is pointing towards the center. This is always true for circular motion. The acceleration points towards the center. So, acceleration of objects in uniform circular motion, it's always pointing toward the center. The last little thing, there is an equation for this centripetal acceleration. We're not going to derive it. It kind of takes a bit of geometry that we're not going to get into. It's not worth our time. The equation for centripetal acceleration is v squared. That's the velocity that object has, and probably v tangential. Okay. Again, it's usually the same because we're saying the speed, the number is the same throughout. But the velocity of that object squared divided by r. That's, again, that radius. So there is an equation for centripetal acceleration. So that's important. This is on the AP Physics 1 equation sheet. The other thing that's important to recognize, this acceleration always, vertical circles, horizontal circles, even if it's not uniform circular motion, the direction is always pointing towards the center of that circle, okay? All right, that's the end of this first video. In the next video, we're talking about and we're applying Newton's second law. But that's it right now. See you later.